Hello again YouTube, it's me Kenny. I'm here with section 1.3 Vector Equations. Today I'm going to cover what the book means by Rn, linear combinations, and a span of a set of vectors. This video may be one to refer to a few times because I've had to use the definition of span of a set of vectors several times throughout the book. Now the important vocabulary that I'm going to be using is vector, scalar, zero vector, linear combinations, weights, and a span of a set of vectors. Now, what I'm going to do is for Rn, I'm going to start talking about R2 instead, bring you up to speed with some vocabulary, and work my way up to Rn. Now, when we say R2, this is what we're talking about, just R2. Now, the R stands for real number. And the 2 just stands for 2 entries. So, if we were talking about R3, it would just be 3 entries. So R2 looks like this, a vector as such, 1, 2. And R3 looks like this, with 3 entries. That's all we mean by entry, or R2 and R3. Now, a vector is pretty much just a matrix made up of only one column. And I'm going to copy the book and refer to a vector as just a list of numbers until about chapter 4. Now I'll quickly cover vector addition and multiplication of a vector by a real number. Now for addition, if we get a u that equals 2, 3, and v that equals 2, 5, I'm just lifting this up almost directly from the book, I believe, if I didn't make it up, then u plus v is equals 2 plus 2 and 3 plus 5. All you do is add right across. And that becomes 4 over, what did I put down? 8. Alright? Now I'm going to go on to multiplication by a real number. This is called also called scalar multiplication. So if we get a C, there we go. If we get a C that equals 5, and a u that equals 3, negative 1, then cu is equal to 5, 3, negative 1, and you multiply each entry by the scalar, which in this case is 5. So we're left with 15, negative 5. Now these two hold true for vectors with more than 2 entries. So for R3 and Rn, it holds true. Now I'm going to go into geometric descriptions of R2. Now this is very easy since we only have 2 variables. We can actually draw it in x1, x2 plane. So let me show you what that means. This would be the x1 plane, and this would be x2 plane, just like an xy plane. So it should be very easy to just get the hang of it. Let's say if you want to draw 3, 1, it's just like drawing a line. Get 1, 2, 3, and 1. And so you draw here, you would draw it exactly as if it was a line, but instead you use an arrow symbol. And that would be your visual description of vector 3, 1. Let's see. As a side note, if you wanted to add another two vectors together, let's say you wanted to add 2, 2. First, you would draw both vectors, 2, 2. And then you would draw a parallelogram. So this would go in this direction, this would go in this direction, where these two meet to make that parallelogram is the addition it is the addition of both vectors. That would be, if this is if I want to call this u and I want to call this v, this is u, this is v, this right here, this middle vector, which is at the other end of this parallelogram, would be u plus v. I'm not sure if that's easy to see. It's kind of hard to see on my computer whether or not this is picking up easily. But I think it's done a good job so far. So I might not have to change that. Maybe just draw closer to the middle, which I'm trying to, but it can be a little bit difficult. Anyway, you probably won't need to draw. You probably won't need to draw out that parallelogram all that often. So now I'll just move on to R3, and as I said, everything holds the same, except that R3 means that you have 3 axes. So that would be kind of like if you were able to start drawing like cubes and spheres and stuff. Kind of. And then we can move on to Rn. So Rn, everything holds true, just like R2 and R3. Rn just means that there are n entries. And you could keep in mind that there could still be a 0 vector, which would be the vector with all zeros and all the entries. Okay? Now the book goes as far as to give you the algebraic properties of Rn. Let me give you that. Here we are. Here are all the algebraic properties. You could take a nice pause for that. Now, I'm not going to actually try to explain any of these or give you examples of these, because I believe it's actually very straightforward. Like, if you know the regular algebraic properties, then you will find that this is rather intuitive to you. Pretty easy and easy to get a hang on. Yes. The only problem is that you just can't cross-multiply 2 vectors, and I'm going to cover more on cross multiplication and dot multiplication later on in later sections. Okay, that was the easy stuff. Now let's get into some of the more nitty-gritty, the more complicated stuff. First, I'm going to give you the definition of a linear combination, since that's important. So here we are. Given vector v sub 1, comma v sub 2, all the way to v sub p in Rn, and given scalars c sub 1, c sub 2, all the way to c sub p, the vector y defined y equals c sub 1, v sub 1 plus dot 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 plus c sub p, v sub p is called a linear combination of v sub 1 all the way to v sub p with weights c sub 1 all the way to c sub p. Now it's really self-explanatory if you really get down to it. The thing that I took away from all this was whenever you see this, whenever you see this, that's a linear combination of this. That's all it is. And you have your weights. And here are your weights. In the beginning, this might seem a little bit scary, but only because it seems a little bit wordy. But as you go along, you'll get used to it, and you'll find that these definitions are usually as simple as possible to be understood, because that's what we want. We want a more exact language here, because math is a science, and science loves exact things and exact language. So there's very little to no confusion. So now what I'm going to do is go to example 5 in the book, which sheds a little light uh, on what the homework and later sections will be asking for. Let me scroll down. Now it goes as follows. Let a sub 1 equal 1, negative 2, negative 5. A sub 2 equal 2, 5, 6. And B equals 7, 4, negative 3. So the question asks, determine whether B can be generated as a linear combination of A sub 1 and A sub 2. That is, determine whether weights x sub 1 and x sub 2 exist such that x sub 1 A sub 1 plus x sub 2 A sub 2 equals B. So I'm going to write that last part down. I'm going to actually write down what it says. Determine whether weights x sub 1 and x sub 2 exist such that x sub 1 A sub 1 plus x sub 2 A sub 2 is equal to B. So here we run into the whole term generated. So what do we mean by generated? I know it might seem self-explanatory, but it wasn't self-explanatory to me when I first encountered this. In fact, it plagued me while I was going through most of the course load. So I'm going to repeat this later in this video. What do we mean when we say generated? Well, the book means that we can use our vectors being multiplied. So here are our vectors, the A, being multiplied by our weights, x sub 1, x sub 2. So we could get some scaled vector. So what do we mean by scaled vector? Well, we already covered scalars, right? So a scaled vector, if I wanted to get well, half of vector a sub 1, x sub 1 would have to be half, right? And so you could say that a vector, that vector half of a sub 1 is a generated, I'm losing my words here. Half of a sub 1 would be generated by the multiplication by x sub 1 being half. Now, if x sub 1 would be if x sub 1 is let's say 1/4, then that 1/4 a sub 1 would be generated by that x sub 1 a sub 1 with x sub 1 being 1/4. Do you follow me? I ask, even though I'm in a video and you can't actually respond back to me, ha ha ha. But I believe that sheds a little bit more light on what we start meaning by generated. So let me catch up to my notes. So one thing that we notice, if B is on the right side of the equal sign, then the linear combination on the left of the equal sign must be able to generate B. And that is what we're asking in this question. Determine if B can be generated as a linear combination of A sub 1, A sub 1, A sub 2. So I covered generation. So in the end, what we're looking for is something that makes this side, that is some x sub 1 and x sub 2, that makes the left side equal B. So we're left with something that looks like B equals B as soon as we test it. But throughout, pretty much a B equals B situation. Anyway, so here we're looking for the weights x sub 1, x sub 2, while a sub 1 and a sub 2 are the vectors. So if you want to write this out, we already did, it's this. Well, actually the linear combination, we wrote this part out. So if we want to write this out using our vectors, we get x sub 1, 1, negative 2, negative 5. So x sub 1 multiplied by the a sub 1 vector plus x sub 2 multiplied by our a sub 2 vector, 2, 5, 6. And that is equal to our b7, 4, negative 3. Maybe I've been writing a little bit too big. Now I don't have any space. Complain. Anyway. So now we're left with this. And it's not quite familiar to what we know, but it is kind of similar because we have scalars and we know about scalar multiplication. So let's go ahead and do that. So x sub 1 multiplied by this is x sub 2, 2 negative 2 x sub 1, negative 5 x sub 1, plus 2 x sub 2, 5 x sub 2, and that is a 6 x sub 2 equals 7, 4, negative 3. Then what we could end up doing is that we could just write this out as a system of linear equations. So we end up with x sub 1 plus 2 x sub 2 equals 7, negative 2 x sub 1 plus 5 x sub 2 equals 4, negative 5 x sub 1 plus 6 x sub 2 equals negative 3. And then this looks familiar enough. In fact, we could write this in the augmented matrix form. So that would be 1, 2, 7, negative 2, 5, 4, negative 5, 6, negative 3, with a nice dot, dot, dot in the middle. There we go. And, well, for now, all we know how to do, the only thing we know to do with an augmented matrix is use the elementary row reduction operations. So we could go ahead and do that. In fact, I'll leave that as practice for you guys. And I'm going to go right to the end. So that would be equal to the row reduced echelon form of this, what I'm writing down now, this matrix. Okay? And so this means that x sub 1 is equal to 3 and x sub 2 is equal to 2. Because we were able to find a solution, we find that B is indeed a linear combination of A1 and A sub 1 and A sub 2 with weights x sub 1 equals 3 and x sub 2 equals 2. Now, notice when we've written out our augmented matrix right here, you see that it is just the vectors a sub 1, a sub 2, and b. Right here, see? A sub 1, a sub 1, a sub 2, a sub 2, and b. So that means we could have just skipped the first 3 steps and just went and written it down as such, and then followed through to get this result. From that, we could actually get this fact that I'm going to put on screen now. Here we go. Fact. A vector equation x sub 1, a sub 1 plus x sub 2, a sub 2 plus dot 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 plus x sub n, a sub n equals b has the same solution as the linear system whose augmented matrix is a sub 1, a sub 2, dot dot dot, a sub n, b. In particular, b can be generated by a linear combination of a sub 1, dot dot dot, a sub n, if and only if there exists a solution of the system of linear equations corresponding to a sub 1, a sub n, dot dot dot, a sub 1, a sub 2, dot dot dot, a sub n, b. Now the second part is just saying that b can be generated by a linear combination a sub 1, dot dot dot, a sub n, if you can take the linear combination, put it into an augmented matrix form, and row reduce it to reduced echelon form to find if there exist solutions for the x values. Keep in mind that up to this point we haven't done much that is new. All we did is add one extra step before reducing to reduced echelon form and seeing if there is a solution. The question we just asked just looks a little bit more complicated than the questions we used to ask. Okay, I know this is a lot for you to digest, and this part is still not over. I wouldn't blame you if you need to catch your breath at this point. That's okay. You could have paused at that moment. So if you're okay, let's keep moving on to that last part. Okay, here is the definition of a span of a set of vectors. Let me put it correctly in frame. Now it states if V1 all the way to Vp are in Rn, then the set of all linear combinations of V sub 1 to Vp is denoted span V sub 1 to Vp. This is called a subset of Rn spanned or generated by V sub 1 all the way to V sub p. That is, the span of V sub 1 to V sub p is a collection of all vectors that can be written in that form. C sub 1, V sub 1 plus dot 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 plus C sub p, V sub p with C sub 1 all the way to C sub p scalars. There's that term again, generated, that I want to call to your attention. Do you remember what that was? Hope so. So what I understood is that for a span V sub 1 all the way to V sub p, there are all linear combinations. Now a linear combination is, let me write that out. A linear combination is y equals, let me see if I got this right, c sub 1, b sub 1 plus dot 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 plus c sub p, v sub p. You already know this, and it makes a good job at describing all other possible linear combinations because all the scalars can be substituted by any number. So all of this could generate pretty much all this could generate all linear combinations, pretty much. Because you could put any C1, any CP, any CN that you would like, and that would get you any combination of the scaled vector or vectors. Anyway, then it makes sense to me to call the possible new values found from the multiplication of the linear combinations, that is, these multiplications of the linear combinations, to be generated or spanned. So once again, I'm repeating myself. That whole idea of generating and spanned. So now with this new insight, I'll just echo what the book said with this insight. Let's see. The span of v sub 1 all the way to v sub p is c sub 1 v sub 1 plus dot 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 c sub p v sub p. I should have used an equal sign. And this is such for it contains the set of all linear combinations of v sub 1 all the way to v sub p. I'll write that out. Contains a set of all linear combinations of v sub 1 all the way to v sub p. It also the definition also added, and it is a subset of Rn. Okay. So the book, oh my god. Technical difficulties, hold on. There we go. So the book, without a pause, goes on to say that if you wanted to know if there was a vector that is in the span of v sub 1 all the way to v sub p, then you're asking if x sub, I'm sorry, can you see that? X sub 1, v sub 1 plus dot 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 plus v sub, I'm sorry, x sub p v sub p equals b has a solution. The idea is that this is the span. This should hold several vectors. B is a vector. If it is within the span of v sub 1 all the way to v sub p, then it could be generated by these guys, and you will get a B. So you'll end up with something that looks like B equals B. And you could even test for that once you're done looking for your X values or your solutions. Now, that sounded very familiar to when we wanted to determine if B can be generated by a linear combination of some vectors, doesn't it? Anywho, the procedure then becomes, let me actually write this down. Let me write down the procedure. Procedure then becomes 1. Write out vectors in the form of linear combination. I.e., in other words, x sub 1, a sub 1 plus dot 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 plus x sub 2, a sub 2 equals b. Then number 2, write in augmented matrix form. Number 3 would be row reduce into echelon form, into reduced echelon form. So to solve for x values, x or c, sometimes c is used in place of x. I'm not sure if you caught that earlier on, but yes, and there's no change to what we're talking about. It's just letter difference or variable difference. Anyway, so solve for x values for determine if there exists at least one solution if at least one solution exists, then B is in the span of, of V sub 1 dot 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 B sub P. Phew. So for extra points, you always like extra points, especially on a test, right? Or at least being able to check your work, right? So I'm going to add number 5, substitute solutions into original linear combination. And see if it equals B. Oh, goodness. That was a lot for me. That was 34 minutes of my time and your time, hopefully, if you still stuck through this. Now, I'm not going to cover the last 2 sections of 1.3 if you have the book. The last 2 sections are have to do with the geometry and the linear combination applications. Neither would really impact the way you understand the rest of my videos or the book. So I'm just going to leave those out. This video is as long as it is. So for now, I'm going to leave you guys. what I wanted to do in the beginning, which I did not have a chance, was to put in a description where everything was and say it out loud, but I wouldn't know beforehand where everything would be until I finished production. And, well, I guess I'm just ranting now. I'm not doing anything beneficial to you guys, not beneficial to my channel. Oh my god, what am I doing? Oh, wow, silly, right? Anyway, I'm gonna just leave you with maybe some good vibes. I hope that everything goes well in this chapter for you. And, well, that's everything. Uh, bye.